Kinematics, the next lesson, the most important lesson. Today, of course, we'll be dealing with introduction only, of course, which is very important. Okay. Kinematics of a particle. Whose picture you see there?
Galileo.
Yes. Anytime you start a physics lesson, especially the kinematics, you have to remember Galileo. There are other people as well, Kepler, Galileo. These two, of course, are credited with starting of the branch called kinematics. There were other scientists as well, including Descartes. But these are the two persons who converted things into mathematical form. And Newton, of course, took it to the next level. Okay, but I'll be talking about kinematics according to Galileo and Kepler later, but let me continue. Yes. Then there's another fellow called Ampere. He is the person who is once again credited with the naming of the word kinematics. He gave it in French, but that converts into kinematics in English. Okay. But let me tell you the synopsis. That's what we are going to do in the lesson called kinematics. All the different lessons under kinematics. Okay. Yes, the heading is, as you keep writing there, kinematics of a particle. You'll be writing along with me. I'll be continuing to talk for some time. Number one, the meaning of the words kinematics and particle. Have you got any idea on your own? 2. Translational motion. Rotatory motion or rotational motion. And motion in general or general motion. 3. Reference frame. Inertial frame of reference. And non-inertial frames of reference. Actually, without the idea of reference frames, physics will be meaningless, children. Okay, can I continue? I hope you're all writing.
Yes, sir, 1 minute.
Yeah. Like this, in every lesson, in every unit, subunit, we'll be defining it in advance as to what we're going to do. It's a very highly structured, but at the same time, there's a lot of room for creativity as well. In the beginning, I sent you one primer. In that, I already defined what is there for 11th class, what is there for intermediate first year. So that only we'll be following. And once again, in each lesson, I'll be giving you things in advance like this. So that provides a proper framework for you to work with. Then Fourth one.
Sir, can you go back for a
Yeah.
second?
Yeah, sure. And remember, this is going to be your notes. In the beginning, I told you, I want you to write them in a proper notebook, a bound white pages, a branded, durable notebook. This will be your textbook. The material is this actually. People keep asking parents all the time. Material. Study materials, they mean. The study materials with us are dynamic, flexible. It all depends on how you respond to it. So this lesson is what you're writing in your notebook will form your textbook. And the assignments will form your workbook. Okay. And the assignments keep improving in terms of their level as you keep responding. Once again, it is a very dynamic kind of a thing. Okay, don't say I don't have a small book like this from which questions keep coming and I'll finish them and say my homework is over. Never your work is over. Never your a lesson for you is over anytime. But all the time you are in a position to attempt an exam or whatever. So that kind of a very broad-based approach you need to have in spite of having some structure like this. Okay, now fourth, distance and displacement vector. Distance is separate, of course, and displacement. For the word displacement, I'll add the word vector. So instead of saying distance is scalar, displacement is a vector, I'll say distance and displacement vector. And in fact, we did it already, no? Delta R is equal to R2 bar minus R1 bar, isn't it?
R1. Yes.
Right. So that
Yes,
only,
sir.
but we'll talk about that again here. And from there, we develop few ideas. Here, average velocity vector, average velocity vector, and instantaneous velocity vector. Those who are attending from the beginning know that I've talked about this average velocity and instantaneous velocity in the lesson called derivatives. We did
Yes,
some
sir.
maths for physics, right? But
Yes,
now
sir.
we'll bring more physics flavor to it while we talk this. That means there actually we went a little logical only. Not much of physics was discussed. So here we'll talk about physics also. Huh? But we connect it to actual physical events. Now, after this, average acceleration vector and instantaneous acceleration vector. Right? Next, equations of kinematics in one dimension with a constant acceleration. A lot of problem solving here. Okay. Then equations of kinematics in general form. That is in 3 dimensions in vector form. And anyway, for every heading from now onwards, there will be numerical problems to be done. Okay. Here I'll include the problems of variable acceleration as well. That's why I put a general form here. This will take care of what all we try to do with that. Okay. Then motion under gravity. With constant g in one dimension, of course. That is, we talk about stones projected up, drop down like that. Okay. But here with constant g. And when we said motion under gravity, the discussion is actually small, but there'll be a large number of applications, that is problem solving here. Okay. Shall I continue, children?
Yes, 1 minute, sir.
Yeah. Then may I continue?
Yes, sir.
All right. Motion under gravity with a constant g, but in 2 dimensions. Motion under gravity with a constant g, of course, in 2 dimensions. This is popularly referred to as projectile motion. Then we did the next topic already in vectors, but we'll be elaborating it here. That is resultant motion and relative motion. Okay. And the last one, most important one, kinematics of circular motion. So after finishing this lesson, you should be becoming comfortable with the ideas and the applications of kinematics under these 12 headings. And remember, kinematics is such a nice lesson because it will get you into the culture of physics. It will get you into the culture of thinking physical events in mathematical terms. There's a lot of difference between popular physics and practicing physics. Popular physics is just very loose and broad. What you read in newspapers. Anybody can talk anything, but it has its purpose. If suddenly people are pushed to serious mathematical kind of a talk, they'll be discouraged to do physics. So the popular physics has that motivational aspect, right? Once you are motivated into physics through popular science, next you should realize that it has to be converted to mathematics. So kinematics is one lesson actually, which helps you think in mathematical terms about the nature around you, the inanimate, the non-living nature around you. So keep listening to me with all the attention, but as you know, you can keep raising your hands and keep asking doubts as well. Okay. So shall I continue, children?
Yes, sir.
Yeah. See how much we'll be able to finish today. You already have the headings with you. We are talking about the first heading, the meaning of the words kinematics and particle, right?
Yes,
Do
sir.
you have any idea about kinematics and particles? Sai, Takshil.
I don't have any idea about kinematics, sir.
Huh?
I do not have that much idea about kinematics.
No problem. Just listen to me. Kinematics. I'll write the word here. It has got this MA here, right? In the middle. Huh? So
Yes, sir.
you discuss the motion without this MA. That's what you call kinematics. I don't know whether you understood. Huh? To study the motion or the branch of physics which studies the motion. Huh? Without any reference to what? Force. Remember, force is the reason for change in motion of a body. I don't
Yes,
say
sir.
cause of motion, but I'll say change in motion. Words have to be used carefully in physics. Without a reference to force and as well mass. Mass of what? Body. And
Body.
force acting on the body. So we don't require to know the force there. We don't require to know the mass there, but still we'll understand the motion. We'll study the motion. Okay. So that branch is what we call kinematics. And I told in a lighter vein, without MA. What is without MA? MA is force, right? Hello.
Yes, sir. Yes, sir.
But what do we do in this? Huh? What do you mean by studying the motion? We study one, position, two, velocity, three, acceleration, etc. of a particle as a function of time, mostly. We use derivatives and integrals to do this, basically. So studying the motion means what? There should be something. In physics, everything has to be put in very, very clearer terms. So we study the position, we study the velocity, we study the acceleration. ETC I put because I'll add keep adding a little more as we keep talking. But these are the main ideas of a particle. I did not say what's a particle, but you can think there's a body as a function of time. You can also write path. That's why ETC I put position, path of a particle, velocity of a particle, speed of a particle, acceleration. All these things without any requirement of force. Though later in dynamics we introduce the idea of force, here you don't require to do. Okay, so that's what we do in kinematics. Not only that, we connect we connect these properties of different particles or two particles, properties of these properties of many particles. This is what people do in kinematics. But you may be worried, what do you mean by that? We can straight away take a question and do it, actually speaking. If you finish it, I'll continue, children.
Yes, sir.
1 minute.
Yeah.
Yeah, done.
Right. Of course, we were given these equations of kinematics already here in the derivatives and integrals I've given you, and some people might be knowing it from their schools. Or I'll remind you about those formulas. But remember, I'll just give a question here to make you understand what we do. A body of mass 2 kilograms starts from rest and moves with a constant acceleration of 2 meters per second square in a straight line. Calculate one, velocity of the body at 5 seconds. 2, displacement of the body at 5 seconds. Here, this mass is given, but that is just destructive, nothing else. In kinematics, we don't require it. We have two equations, V equals U plus AT and S
AT.
equals UT plus
UT
half
plus half AT square.
AT square. So this is what you mean by kinematics in a very, very practical terms. So V equals starts from rest we said, right? So 0
Yes.
plus A is 2 meters per second into time. How many seconds? 5 seconds. 1 second cancels. I'll get 10 meters per second. S, U is 0. So half A, 2 meters per second into T square. 5 into 5 second into second, right? Cancels. What will I get? 25 meters. So this is what you mean by kinematics in a simple way. I told you already, the mass may be given here, you don't require it at all. And you don't even know why the body is accelerating here. In future, you will know that the body will accelerate because of the application of a force. Do you follow?
Yes, sir.
Right. Now, I'll come back to this again, but meanwhile, let me discuss what a particle means. You can also say that you're connecting the kinematics of two particles. If I remember, I've done one question. Like there is a lamp here. And a person is walking with a speed V1. With what speed does the shadow move?
Yes, sir.
This is connecting the kinematics of two things. One is the person and the second is his shadow.
Shadow. Yes.
So once, of course, for this, you don't require serious things. Do you remember as to what we did? Hello, it is given that this height is h, the person's height is h. And V1 is given, h is given, h is given. We would like to know the velocity of the shadow. this is a shadow. I did not put the whole thing. Hope you understood it. Have you? Huh? Hello.
Yes, sir.
So what do we do, Ganesh, here? Question 1, this is question 2. See, in physics, we don't speak waste words. Here, we said, we study position, path, velocity, acceleration of a particle. We said, then we connect the properties, such properties of many particles, we said. So to explain that, I was actually doing these 2 questions. Okay, here we found velocity, we found displacement, for example. Path, we did not find here. For that, we require some extra information there. But in the question itself, we said it is moving a straight line path. So there's nothing to find out the path, right? Hello?
Yes, sir.
Huh? Now, what do you do for this, Ganesh? This question.
Sir, like we can take from origin to
This is the origin, we'll think. This
That-
distance is
up to there as x, sir.
x1, we say.
X1, yes, sir.
This is say. This is not given in the question. Huh?
Yes, sir.
Whatever you say now like this, whatever you suppose are there should be removed later. Your answers must be in terms of what are given in the question. And this one is
X2.
x2. Position of this.
Yes, sir.
Right? So what kind of a mathematics we would write, Ganesh? From the properties of similar triangles.
Yes, sir.
Tell me. You can draw one separate figure if you want to make it easy.
Sir, so x2 is to height of the post will be
Yes,
equal
this
to
is h, this is h, this is x1, this is x2,
X2. Yes, sir.
right? So this is x2 minus x1,
Yes, sir.
isn't it so? So now can you tell me what should I write for the mathematics? I'll write at the top with a different color. Can I write like this? Hello, why don't you
Sir.
people tell me? X2 minus x1 by h. Which triangle did you say?
The small one.
Probably I've written cot theta, if you want in trigonometrical terms, is equal to, for the bigger triangle, x2 by h. Hello.
Yes, sir.
Isn't it so?
Yes, sir.
We need to write for x2 here. We need to write for x2 here. Hello. So what do I write for x2? You should be able to give the maths quickly, actually speaking. x2 in terms of x1, I should be able to express. I wrote this distance by this distance is equal to what? This whole distance
X2 by h.
h I wrote.
Yes, sir.
Hope people followed it. Without calculating it too much, you should be able to write, but anyway, I'll calculate. People are not saying anything. hx2 minus hx1 is equal to hx2. So what do I get? h minus hx2 is equal to what? hx1, right?
Yes, sir.
Now differentiate on both the sides with respect to time. Isn't it so? Hello.
Yes, sir.
H minus h into dx2 by dt is equal to what? H into dx1 by dt. So what do we get for dx2 by 2? dx2 by dt is what, you know? The speed of the shadow tip, isn't it? So v of the shadow equals h into dx1 by dt is velocity of the person, right? Speed of the person.
Yes.
v1 by h minus h. This is what we mean by connecting the velocity of the person to his shadow. The person can be taken as one particle, the shadow can be taken as another particle. So we made a statement previously that in kinematics, we'll find out a few things of a particle, but we'll also connect few things of different particles. Okay. So here we're not discussing the cause of motion, force, nothing, right? In a way, it is a little mathematical, this lesson. In fact, nowadays, kinematics is once again very, very important in applications, especially when you talk of robotics. The robotic arm, for example, requires a lot of kinematics. Kinematics of translation, kinematics of rotation. As this hand moves and as you move forward, it's all complete mathematics there. In fact, people say kinematics is a branch of mathematics or geometry, for example. Most of you, some of you at least, maybe after doing BTech or even during your engineering, might be interested in robotics. Okay. So what you learn now really is going to help you in a big way later if you really understand it and do it. Of course, not, mug up once again. All right, can I continue?
Yes.
No, why I did this question is for some people who missed it, it's once again a reminder here. Okay. All right. May I continue?
Yes.
But remember, kinematics is basically, the way it is discovered is basically experimental. Kinematics way of studying the body was initially discovered in experiment. I named two persons, Galileo and Kepler. Kepler did not do experiments, of course. He just used the experimental data collected by his master, Tycho Brahe. Remember, because I'm talking all this, don't think this is not IIT, JEE, Maths or whatever, because nowadays people simply start something without any meaning. If you understand the subject this way, you have a purpose of doing things. Otherwise, many students get bored and discouraged because they don't know what they are doing. So here, I told you, kinematics way of studying the motion was initially discovered in experiment. By whom? By Galileo or by Kepler. What did Galileo do? He did many experiments. What kind of experiments, you know? Inclined plane experiments. Pendulum experiments. And many more, of course. These are the most popular one. He did not do experiment, but he collected the data by watching the sky for years, from 15 years, 20 years, I don't remember, with no telescope or nothing. He set up an observatory somewhere, and he was an enthusiast. He was not a scientist or a mathematician. He was a rich uncle's adopted son who was very aggressive in the beginning, but later developed interest in the celestial things, and he collected a large amount of data. And this fellow Kepler was a poor fellow, but very intelligent fellow, knew mathematics. So he used that data. framed 3 laws of planetary motion. What are these 3 laws, children? I'll just mention it because we'll be discussing that in great details later in gravitation. But basically, remember, these 3 laws are kinematics of planetary motion. Right? What are these 3 laws? According to him, all the planets, every planet revolves around the sun in an elliptical orbit. So this is about the path, right? At that time, they did not even know that. Of course, they knew, they have an idea of force, but they were not very sure of what kind of a force. Now we know there's a gravitational force. Now means Newton, of course, introduced that idea. Gravitational force will keep acting and keep turning the planet. But he basically talked about path of the planet. And next he said the time period of the planet. He said some law, he gave some law, t square is proportional to some a cubed. This is called 2a for the ellipse. So half of it, 2a is the major axis, people say. So t is time period, time for one revolution. Actually, this is the third one, sorry. This is the third one. And second one is the aerial velocity is constant, he said, dA by dt. The rate at which the area is swept by this planet around the sun is constant, he said. Some L by 2m, whatever. I'm not giving that now because that will be a new word once again for you. Angular momentum by 2 times the mass of the planet. So here, this is about areas. This is about time period. And this is about path. So nowhere here the gravitational force is mentioned. Try to understand. So that's why it is called kinematics. No reference to the force, which is the reason for this kind of a motion. So laws of kinematics were basically laid by Kepler also in the beginning. And remember, Newton actually took from here. Newton actually, he wanted to tell why these laws are correct like this. Therefore, he discovered 2 laws, F equals ma and F equals g mm by r square, because among many things, these 3 laws were very important to be explained. So Newton actually had to frame these laws partly to explain why things happen like this. And Galileo himself, by doing these inclined plane experiments and pendulum experiments and a few other experiments, gave us 2 important laws of kinematics. One is S equals half some, I did not even say half gt square, but some constant into t square for free falling bodies. Free falling bodies means those bodies which fall with 0 velocity. And also from there, he said v equals some constant into t. Okay. So these 2 laws, basically, which we derive as equations and keep applying them, were actually given by whom? This fellow called Galileo. Hello, are you listening?
Yes.
Yes, sir.
Amarnath, are you there?
Yes, sir.
Are you listening?
Yes, sir.
Or are you thinking,
Yes,
why
sir.
sir is talking so much? Why can't he start problems straight away? Are
No,
you
sir.
thinking? No.
I don't think.
You're understanding this, right? Okay.
Yes,
But
sir.
look, the whole thing is talked in pure mathematical terms like this. Do you follow? Huh? Okay.
Yes, sir.
Yeah. Kinematics is basically from experiment. People did experiments, and the results of the experiments they formulated into mathematical equations, which are called, for example, laws of freely falling bodies. These are what? Laws of planetary motion. This we don't do right now. We'll do it in the lesson called gravitation. But remember, this actually kinematics laws there. Kepler did not know means definitely they had some idea of force, but force was defined later by Newton, not Kepler. Newton used all those great fellows' ideas and systematized study of nature into a subject called physics. Okay. Vasist,
Yes, sir.
are you okay with the whole thing?
Yes, sir. Yeah.
Right. Now I'll further continue, children. I've not addressed that word called particle yet. Okay.
Yes, sir.
Can I move it?
Yes, sir.
Yes, sir.
Latshab. There's one fellow called Dhanush Chandra. Are you there? Because the numbers came down again today. I don't know what parents are doing. They should make them sit at least near the system. Minimum. Of course, they cannot force them, but all right, I'll continue. Dhanush Chandra, are you there? Damodar? Just 1 second. So what is a particle? Next thing is particle. I'll just give a small statement for that. There's no definition like thing. Definitions in physics will be in mathematical form. I'm telling you, this is the meaning of the particle, word particle. An object of matter. Without any internal structure. But remember, this is basically an approximation. People say it's a point mass also. This is what I mean by particle. Any questions? I'll continue. Look, I want to justify this approximation by going to the next thing. Translatory motion or translational motion. Can anybody say what is this translation about? If a body's position alone changes, without any change in its orientation in space, it is said to be making translatory motion. Many people misunderstand translational motion as a straight line motion. It can be straight line or rectilinear, you can say. or curvilinear also. You may say what it means. You may have a motion like this of a body, or you may have a motion like this. Both are termed as translatory motion here. The defining property is this: position alone changes without any change in its orientation in space. To put it bluntly, there's no spinning happening. There's no spinning happening. If there's a block like this, for example, here, this block is moving like this from there to here. Every particle in the block has same properties. The displacement of this edge is same as the displacement of this edge, for example. This is a solid body I took. It's a wooden block, for example, which is moving from here to here. That is, the position is changing from here to here without the body spinning in the middle. That's what we call translatory motion. Do you follow? Hello?
Yes.
And this also you can think. Some block may be just moving like that. Okay. So there also, there's no spinning in the middle. But if you want to put it in pure mathematical form, look, to tell what is rotation, I'll tell this is, look, without any change in its orientation in space means without any rotation, without any spin, we mean to say. Look, motions in general, in practice, are not pure translation or pure rotation. If I throw this phone like that from here, the phone's position changes from here to there. That's what you mean by translation. But as the phone moves, it keeps spinning like this, isn't it? So that's what you mean by general motion, a combination of translation plus rotation. So rotation means what? Now, rotational motion alone, if you would like to understand, what is that? You know, it is the orientation alone in space changes, but not the position. Okay. Orientation in space alone changes, but not position of the body. You can think as many examples as possible. A compact disc just only rotates. A fan only rotates. Do you follow? Huh? But the wheel of a moving automobile translates and rotates. And a block just pushed along the table only translates. Do you follow? And why did we bring these words translation and rotation here? Remember, though we have practically big bodies like this, in translation motion, I can think the body to be a particle. Though we said a particle is about an object of matter without any internal structure is or a point mass is a particle. There's nothing like in the day-to-day life we deal with point masses. Do you follow? In the day-to-day life, we'll approximate a body to be a particle if it is undergoing translatory motion. That means if it is not spinning as the body moves, if it is only just sliding as a single body, since the particles, since it's different points, the body are having the same properties, we can simply think of crumpling the whole body into a point mass at a particular point called center of mass of the body. I use a new word, center of mass. But center of mass will be always a point mass. That is, I told you, if there's no difference between the velocity of the front and back. There's no difference between the velocity of acceleration of the front and back of the block here. I just can simply ignore the shape and size of it and simply say that it's a point mass moving from here to there. So our life becomes easy while dealing with emotion. Can you say something? I've been talking continuously. Hello. So we discuss kinematics of particle now. Later we discuss the dynamics of particle now. That means even when you apply F equals ma, remember you're applying it for the center of mass. Center of mass, whatever it is, don't worry. Or you can say a point where you can supposedly think that the total mass of the body is concentrated. So what I mean to say is we discuss about a particle until we go to a lesson called rotational dynamics. So much, so many things happen until we reach that rotational motion, which comes at the end of the mechanics, basically. Until then, we are dealing with a particle. So your questions, please, before I continue. Then, can I just change my screen here? Vishnuvardhan?
Yes.
Yes, sir.
But no questions are being asked. Why? It is becoming very clear or looking scary? Vignesha? Sai Ganesh?
Understood, sir.
Don't ever think that we are doing high stuff here. This is actually the actual stuff.
Okay, sir.
Nowadays in the schools, this has gone for a toss. So translational motion is not straight line motion alone. It can be even curvilinear motion. Do you understand the meaning of curvilinear? That's still a line, but a curved line. It should be
Yes,
a
sir.
motion along a line, curved or straight. That's called translatory motion. That's one misconception you should get away from. Translation motion is not definitely a straight line motion alone. It can be even curved line motion of a body. But as the body moves, it doesn't spin. Actually, people put it in a much more nicer mathematical way. Say this body put body axis. What did I say? Fix access to body. One Z through the depth of it. Okay. As the body moves, the axis will remain parallel to their all the time remain parallel to their previous positions in translation. What did I say? This is body axis. You know, body axis. That means you're actually rigidly fixing this axis to the body. A real axis system you can put, 3 spokes you can put, or you can think of imaginary axis like that. Doesn't matter. But if the body is spinning and moving, this axis keep rotating. Do you follow?
Yes, sir.
This X, Y, Z, if you say, this X, Y, Z will always remain parallel. That's called translation. So this is how, remember, things will be converted to maths. But for example, if I throw a body, no, not throwing a body. If I have a fan here hanging, here put the axis to the what you call blades only. All right. 1, 2, 3 in the same plane only you put. Don't worry. So as the fan rotates, will they remain parallel to their initial positions? This axis also keep changing. Isn't it so?
Yes.
That's called pure rotation. Even when a compact disk keeps spinning, the body axis keep changing, isn't it? Their positions. Hello.
Sir, in curvilinear motion, will the axis remain or change, sir?
In a curvilinear motion, also axis should remain parallel. Okay.
Okay, sir.
That figure I'm not showing because it's difficult to draw.
Okay, sir.
So if when this thing is rotating, this axis now will be there, right? This axis is here like that. It keeps changing, right? So this is what you mean by spinning or rotation. But for example, if I throw, for example, some, say, this table tennis bat is there, no? Just take that bat and throw it under gravity. For my drawing clearly, I'll just put something for my reference in advance. After that, I'll write so that it looks nice. I will throw that thing like that. It may be going like this. It's not easy to draw, but I'm trying. I hope you're all understanding what am I trying to do. Do you?
Yes, sir.
Like that. So what is happening here? There is a translation. Translation of whom, a point called what? Center of mass. It just goes in a parabolic path. But as this body is moving, the body is spinning. Do you follow? Hello? The body is spinning here.
Yes, sir.
So this is general motion. This is combination of what? Translation plus rotation. Here, if I put some axis to the body, the axis won't remain parallel all the time. They keep turning. Do you follow? Pure translation, pure rotation, general motion. It's a combination of translation plus rotation. So look, for this rotation of the body, can I say the whole fan is a point mass? Meaningless, right? Why? This edge of the fan describes a larger circle than this point. So if I simply say fan's rotation can be replaced by a point mass motion, I'll be simply spoiling the whole motion of the fan, isn't it? Hello. But whereas here I can say the block is at this point and moving like that, I can say, because every other particle also does the same thing. The paths will be parallel. This one, or simply parallel. Do you follow? So here the body is made as a particle, not here. All right. Here we'll say it's a particle at the center of mass, but still there's a rotation there. So that's what we're going to do in the next few months. Are you listening?
Yes.
Yes, sir.
Yes, sir.
I think people are dropping out already because they've already given me 3 minutes extra time and did a favor. Okay. All right. So I'll be uploading this video. Please listen to it carefully. I'll be doing, as usual, many problems, but remember, problems cannot be done, should not be done without proper basis. Okay.
Okay, sir.
I'll be closing it for now.
Thank you. Sir.
Thank you, sir.
Thank you, sir.
Bye.
Thank you.